Hello, this is Al from Al's Electronic Classroom, and what I've noticed is that on Facebook and on YouTube and other social media platforms, the authors give you demonstrations of these circuits and what they do. But basically, what I've noticed on a lot of them, not all of them, but a majority of them, is they show you how to assemble them and they show you the interaction, but they really never explain theory of operations. So what I've done right now is I've taken one and I'm going to look inside the component. I shouldn't say look inside the component. I'm going to look at the component. I've pulled a spec sheet, and in the upcoming video, I'm going to explain the theory of operations and why it does what it does in the video. So let's get started. Notice how the solar panel follows the light clockwise and counterclockwise. How does that do that? That's what we're going to talk about. That's what I'm going to explain now. Okay, what I've done is I've redrawn the circuit, or I've given you a schematical representation of the circuit. And basically, what do we have here? Well, this right here, which you can see that there's a daughter. This is a single package. And in this package, we have two components. They're an operational amplifier, but they're working in what we call a comparator mode. And I'll explain that in the next slide. But before we go there, we've got a 3.7 volt battery, and that's basically what he used in the original video when he showed you how to install this. And we've got two resistors. They're both 10K, and we're using these resistors as a voltage divider. And again, I'll get into that a little bit more. We also have two resistors right here, and they're LDRs, which stands for light dependent resistors. So LDR right here stands for light dependent resistors. And the resistances on this device depends upon light. All right. And again, I've got a slide. We'll go into the functionality of that. Okay. So again, this is in one package. There's two ICs, or integrated circuits, in the package. All right. And when I show you the pinouts, we'll notice that the supply voltage goes to pin 2, and we've got ground, or the negative terminal of the supply, that goes to point 4. Now, right here in the video, he put an electric motor, an electric DC motor. I took that out right now, and I'm putting a resistor in there, and there's a reason for it. We'll see as we go. So if you look at the video, he solders, or they solder, and they solder pins and so forth. So what I've done is I've redrawn this into a schematic, and when you see it schematically, it makes more sense. All right, so here it is right here. So let's go to the next slide. Okay, I want to regress here a little bit. Before we go into that slide, here's the circuit in the last slide, and here's the component pinout. In other words, these two amplifiers are in this integrated circuit, and if you look at it, it identifies what each pin will do. 2 is the supply voltage, right there. Whoop. 3, 4 is ground. Okay, notice output 1, input 1, minus input 1, I'm sorry, and plus input 1. All right, so that would be this part of the IC here. And we have plus input 2 and minus input 2 and output 2. So right here and here is this IC. So you can see from the video when we shot pin 6 and 7, and again, maybe that's not correct, 6 and 8, what we're doing here with this package is connecting the plus input of U12 to pin 8 of U11. All right, and we can see right here that pin 8 is a minus input again, and 6 right here is a plus input. All right, so this pinout, and let me erase the slide. This pinout here is unique to not this specific one, but each integrated circuit will have a pinout like this for their component. All right, and again, he's using or what is used in this circuit is a TDA 2822, and there it is right there. So what I did was, I went through the video, I took this pinout or this pinout of this IC, and I looked at it, and I just connected the inputs. And then after I did that, I looked at it and analyzed it to see its operation. So that's how I kind of reversed engineered it. You'll hear that term. So I kind of looked at what it was doing. I looked at the components, both passive and active, where this IC here is an active component. The 10K resistors for a voltage divider, those are passives. All righty. So I looked at them and I just determined the circuit action. So I wanted to show you this first. That's how I constructed the circuit, or reversed engineered the circuit, and I know it works. All right. All right, here we're going to demonstrate comparator operations. All right, and basically, if you look here on this one here, I've got 5 volts and 4 volts, and right down here, I tell you, inputs determine the output. The larger voltage wins. So, I've got 5 volts on my plus terminal right there, and I've got a minus 4 volts on on the negative terminal of this comparator. All right, and the larger voltage wins. So the difference is 4 volts minus 5 volts. The larger voltage, or the difference between the two voltages, and is on the positive terminal of the comparator. So therefore, the output goes to plus V. Let me erase that, okay? So the output goes to plus V, again, because I have 5 volts on my positive terminal, 4 volts on my negative terminal. I take the difference, all right? The larger voltage is on my positive terminal. This forces the output to go high, or to plus V. All right. Now let's look at it when I reverse the voltages over here. I still have 4 and 5 volts, but again, now 4 volts is on the plus terminal, 5 volts is on the negative terminal. I take the difference. Where is the larger voltage? It's on the negative terminal. So therefore, the inputs are going to force the output, or allow the output to go low to negative. Output goes negative, in this case to ground, because if we look at the previous slide, here's my 2 supply pins, 2 and 4. 4 goes to the negative terminal of the battery. So therefore, the highest level, because of the battery voltage, or the supply voltage for the integrated circuit, okay, the highest it can go, the output in this design, Okay, notice I say in this design is 3.7 volts because that's what the supply voltage is. That's the positive rail, what we call the rail on the supply voltage. And on the other end, the negative terminal goes to ground. So my voltage swing on the output can only go from, let's go back, can only go from 3.7 volts to negative, or in this case, 0 volts. All right, so let's stop here and go to the third slide. Okay, let's talk about what this LDR is. It stands for light-dependent resistors. And basically, as we state here, an LDR is a variable resistor that changes its resistance according to the intensity of light falling on its surface. So basically, you can, I'm going to have these slides for download, so you can download, you can actually read the rest of this. But the bottom line, or the crux of the matter is, if you look at this graph right here, all right, nighttime, dark time, in other words, if I take this LDR and I have no light, I put it in darkness, the resistance is going to be high. It's going to be very high, which we show here. And as I bring it out to the daylight or increase the amount of light that's applied to the LDR, it gets lower. So what we can say here is this LDR has a high resistance with the absence of light, and the resistance decreases as we increase the brightness or the intensity of the light. So that is what the LDR is, light-dependent resistor. Again, the resistance depends upon the brightness that is shined upon the surface of the LDR. All right, that's it. That's it. All right, so let's go on to the next slide. Okay, so now let's try to put all this together. All right, so let's look at this circuit. And this is the one originally that I put in at the very first slide when we reverse engineer it. So up here, this LDR, okay, when I'm in dark, which is the absence of light, this LDR has a resistance of 1 megohm, okay? If I shine a bright light on it, I have a resistance of 1K, all right? All right. Now, right here, R1 and R2, all those resistors are doing is providing a voltage divider or a voltage reference to these two comparators. So you'll notice right here, when I do the math, I've got 10K over 20K times the supply voltage, or the battery voltage, in this case of 3.7 volts. When I do that, I get a voltage of 1.85 volts. That's right there. That's static. That's not going to change. So these two terminals of the comparator will always see or always have a reference voltage applied to them of 1.85 volts. Okay, so if you remember from the video, when this little solar panel was going back and forth, what the gentleman was doing was he was shining a light on either one of these LDRs. All right, so let's look at this. All right, we have 7 and 8 of my comparator. They're connected together as shorted. All right, they are also tapped off the junction of the two LDRs right here. So let's see what happens. Now, I can only have two states. When this is bright and this is dark, or when this is dark and when this is bright. Just two states. What happens? All right, so our LDR, we have a dark resistance of 1 megohm and a bright resistance of 1 k ohm. Okay, so that's 1,000,000 ohms to 1,000 ohms. That's about 100 times bigger, and to emphasize this. So across each LDR, depending if I have a light source shined on it or not, what's going to happen is the LDR is either going to be 1,000 ohms or it's going to be 1,000,000 ohms. So let's look at the two states. All right, when the LDR, all right, it has light shined on it, okay, it's 1,000 ohms. The whole resistance of the circuit is more than 1 meg. And again, I've got a typo here that I just realized. It should be ohms, not OHMM. This is a little off, but it's okay. Okay, I'm practical. It's not going to give us that much of an error. So when I'm 1,000 ohms over, let's say, 1,000,000 ohms, all right, for all intents and purposes, the voltage across that LDR is going to be 0 volts. And when I have the absence of light, all right, the value of resistance for the LDR is going to be 1 megohm or 1,000,000 ohms. So I'm going to have 1,000,000 over approximately 1,000,000, which is 1, and I'm going to have approximately 3.5 volts. All right. So in the two states, again, the two states, all right, the LDR, either one, this applies to either one, all right, because if you remember from the video, he took a flashlight and he went from one LDR to the other. Two states, either one had light and the other one didn't, or the opposite one had light and the other one didn't. So it would go from 0 volts across the LDR to 3.5 and 3.5 to 0. Hold it, all right? On the next slide, we're going to look at the states and go through it. Okay, now on this slide, here we go. All right, remember, two states. So now I'm shining, or we're shining the light on LDR1. What's the voltage across it? 0 volts. What's across LDR2? 3.5 volts. Two states, 0 or 3.5. My 1.85 volts is a reference that does not change. We see that on pin 1, on pin 8 and pin 5. Remember, there are two comparators in this one IC. Okay, these are always going to see 1.85 volts. That's my reference. So let's look at what happens here. On this state, I got 3.5 volts. So let's look at here. 3.5 volts, all right, here. Negative on this comparator, all right. What's going to happen? The output is going to be driven low. In this case, since my low point is 0 volts, I'm going to go to 0 volts here. All right, I'm actually going to go to the negative terminal of the battery or ground. All right, and what's going to happen over here? Okay, 3.5 volts, right? Where are we on this one? We're on the positive terminal of that upper comparator. What's going to happen there? It's going to drive this to my supply voltage. I know we've got a 3.7 volt battery supply here, but probably there's going to be about 200 millivolts or 0.2 of a volt drop internally into the IC. So we're going to get about 3.5 volts out of it. So look at what I got on this state. When LDR1 is 0 volts and LDR2 is 3.5 volts, I get 3.5 volts. And again, remember I put this resistor in there, so I'm going to get 3.5 volts DC across the resistor. We talk about electron flow, so electron flow is going from my negative to my positive. So in this case, I can say electron flow is going counterclockwise, all right? We're going counterclockwise. Let me make a note of that. Again, counterclockwise, all right? Let's stop here and go to the next slide where we reverse these two, and let's see what happens. Okay, now on this slide, all I've done, or all we've done, is now we're shining the light on this LDR, which we called LDR2. So what happens? Well, on this one, I get 0 volts, and on LDR1, I get 3.5 volts. Again, pins 8 and 6 of the amplifiers or the comparators are connected together. My 1.85 volts DC reference doesn't change. So what do we have here? So we have 3.5 volts across this one. So what do we see across LDR2? 0 volts. LDR2 is connected to 7 on my top comparator, which is the plus terminal right there, and also connected to my bottom comparator, all right, which is a negative terminal. So let's see what's going to happen. 0 volts. I got 0 volts here. What's here? 1.85 volts, but it's on the negative terminal. This is going to drive this output to 0 volts. What's going to happen over here? Again, 1.85 volts, right? What do we got here? 0 volts, 1.85 volts in my plus terminal. What's it going to do? It's going to drive this output to 3.5 volts. Notice that the voltage across this resistor between the previous slide and this slide, the polarities have changed. So now current flow goes, excuse me, we use electron flow. Electron flow goes from pin 1 of this comparator, and the direction here is clockwise. So we go clockwise here. The previous one, we went counterclockwise, and now we go clockwise. So you can see what happens. The current is changing direction depending upon which LDR is 0 and which LDR is 3.5. And they switch because I only have 2 states. Let's go on to the next slide. Okay, so in this slide here, what I've done is I replaced that resistor with this graphical representation of a DC motor. It's in blue. And here's what happens. There's always 3.5 volts across this. In the previous 2 slides, it was a resistor. Ideally, what he shows in the video is a DC motor. There's always 3.5 volts across it. The deal is which way the current flows. All right, so we can either go clockwise or counterclockwise, and it depends on the direction of the current flow. So when the current flow is flowing in one direction, the motor will turn the this mini solar panel clockwise, and when we shine a light on the opposite LDR, it will go counterclockwise. And that's why he's going between the 2 LDRs, shining a light on them, because what's happening is the current flow is just changing directions, and when the current flow changes directions, that changes the direction of the DC motor, either clockwise, it rotates clockwise or it rotates counterclockwise. And that's how this works. It's not mysterious. It's not magic. It works that way. Now, as far as that solar panel that is placed upon there, there's no connection to that. I think what he's doing is just trying to show you how you can track with the sun. You know, if you place that and with this circuit, there's got to be some adjustments. Yeah, if you build it and put it in the sun, it's probably not going to work the way you think. All right, the light's got to be directed on those LDRs. So anyways, that's it. I hope you liked it. So let's go to the next slide here. And I'm going to invite you to join my Facebook group. What I'm going to do, and I believe I can do it. I'm not that Facebook up to date or whatever. So I'm going to try to put these slides on there. So I invite you to join my Facebook group. Here it is right here. I know it's got that number there. Somehow I can change the name. I haven't really done that yet. So you can use that, or you can just go into Facebook and search on Al's Electronic Classroom in the group section. I also have a Facebook page also, but I'd like you to join the group. I'm gonna place these slides in the group, and I may add something else to this video. I don't know, but I think what I'm gonna try to do, and it's something new for me, as I see some of these things that I see on social media, YouTube or on Facebook or on other social media platforms, where they just assemble them, I'm going to try to reverse them and give you theory of operation and show you and explain to you how it works. Electronic is not magic. It's not this magical thing. There's some physics and there's some common sense stuff. If you understand the components and how things work, you'll figure it out. Anyways, that's it, and I thank you for staying with me through this. It's kind of long, but I hope you enjoy it. If there's some way you can leave a nice comment for me, let me know. You take care. All the best. This is Al. Take care. Bye-bye.